Hello, young physicists. Ever wonder why you hear your friend before you actually see their lips move? That's because sound has its own special speed and it depends a lot on where it travels. Speaking of lips moving, why did the sound wave apply for a job? Because it wanted to propagate itself. Alright, let's break it down. Sound travels as longitudinal waves. Imagine a row of dominoes. When one topples, it pushes the next, and so on. But here, instead of dominoes, we have particles bumping into neighbors, oscillating back and forth, passing energy along like a whispered secret down the line. Now, the speed of sound isn't the same everywhere. It depends on two main things: the medium's elasticity, that's how springy or stiff it is, and its density, which is how tightly packed those particles are. We can sum this up neatly with a formula. The speed of sound, that's V, equals the square root of E divided by rho, E standing for the medium's modulus of elasticity and rho for its density. In words, that's V equals square root of elasticity divided by density. The stiffer the medium and the lighter the particles, the faster the sound zips through. Ready for another lightning fast journey? But first, a quick joke. Why don't light waves ever need a couch to crash on? Because they don't need a medium, they travel solo. Light waves zip around as transverse electromagnetic waves. Unlike sound, which needs a crowd of particles to pass the message, light doesn't need any medium at all. That's why light can travel even through the emptiest vacuum of space, no air, no water, no problem. The speed of light in a vacuum, that vast empty space, is an amazing constant, 3 times 10 to the 8 meters per second. To say it plainly, 300 million meters every single second. Imagine running around the Earth's equator more than 7 times every second. That's how fast light is. But hold on, light's speed isn't affected by temperature or air pressure. It's a universal speed limit. No matter where you measure it, that figure stands firm. Now, when light moves through different materials like glass or water, it slows down a bit. That's because those materials have what we call a refractive index, represented by the letter n. The speed of light inside such a material is simply the speed in vacuum divided by n. That means V equals c divided by n. So, higher refractive index means slower light speed. Imagine a bar chart where each bar shows speed of light in different media: vacuum, air, glass, and water. The tallest bar is vacuum with 3 times 10 to the 8 meters per second, then air slightly less, and glass and water showing noticeably shorter bars. This slowing down doesn't mean light is lazy. It just means it's busy interacting with the material's particles. That's why lenses work and rainbows form, because light changes speed and direction inside different materials. So, when you turn on a flashlight, what you see is light racing through space and materials, always near impossible to beat in speed. The speed of light in air, about 3 times 10 to the power 8 meters per second, is nearly 1,000,000 times faster than the speed of sound, which is about 343 meters per second. This huge difference exists because light is electromagnetic and does not require a medium, whereas sound needs particle interaction to travel. This speed gap explains why, during a storm, we see lightning much earlier than we hear thunder. In fact, the ratio of light speed to sound speed in air is approximately 8.8 times 10 to the power 5. Let's solve an example of thunder delay. Suppose the time delay between lightning and thunder is 5 seconds and the speed of sound is about 340 meters per second. We need to find the distance between the observer and the lightning. Using the uniform motion equation, distance equals velocity times time. Substituting the values, distance equals 340 times 5, which is 1700 meters. That is about 1.7 kilometers. This matches the expected audio delay we observe during a storm. Alright amigos, let's wrap up today's speed showdown with a quick recap. First, the speed of sound depends on the medium's elasticity and density. It's given by this formula: the speed of sound, v, equals the square root of the modulus of elasticity, E, divided by the density, ρ. Remember, that's v equals square root of E over ρ. Second, the speed of light in vacuum is a whopping constant, 3 times 10 to the 8 meters per second. That's a superstar speed, c. But when light travels through any medium, its speed changes. It slows down according to the formula v equals c divided by n, where n is the medium's refractive index. Here's the striking part: the ratio of light speed to sound speed in air is about 8.8 times 10 to the 5. That's nearly 900,000 times faster. No medium needed for light, but sound can't move without one. That's why lightning flashes almost instantly, but thunder lags behind. Remember, sound speed changes depending on whether it's flying through air, water, or steel, while light stays constant in vacuum but slows in denser materials. So, whether it's the roar of thunder or the sparkle of lightning, these speed differences explain much of the magic in our everyday world. That's it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.